Hello ladies and gentlemen, a warm welcome to the latest edition of the Mahlo mCast. My name is Thomas Höpfl and I'm the sales director of Mahlo. Most of you will know Mahlo as the synonym for weft straightening. Mahlo is offering quite a number of different types of weft straighteners, optimized for different types of fabrics, optimized for different applications. But there is one thing which all those machines have in common, and this is our detection system. And exactly this is the topic of today's mCast. If you like what you hear today, you also may subscribe to our YouTube channel. The link will be indicated down here. Thank you. The topic is our detection system. Like we say, it's compact, it's precise, it's working simultaneously. Let's start with the beginning. Mahlo was the one to develop this kind of systems. Already in 1958, Mahlo has installed the first distortion detection system in a textile factory in Germany. Since then, we have continuously optimized and developed further and further our scanning systems, and now we have a huge portfolio of different types of detection systems and sensors which can be selected depending on the fabric which need to be straightened. There is at first our optoelectronic detection system. This is our TK12. This is our most versatile sensor. I would say about 90% of our weft straighteners will leave our factory with TK12 sensors. Additionally, we have also a camera-based sensor. This is our CK15. It is available with reflex light, but also with penetrative light. Both sensors, the TK12 and the CK15, like I mentioned before, they are optimized for different types of fabrics and fabric constructions. So sometimes if a customer is in the need of straightening as well types where the TK12 is optimized for and also where the CK15 is optimized for, then we have a possibility to offer a so-called hybrid scanning system. It consists of both systems. They are joined together and they form a complete new detection system. So with this we have now the possibility to detect the fabric from both sides, and the operator is the one to choose which detection system is the better option for the fabric and the job he has to do at the moment. Finally, we also have a detection system, also camera-based. This is then optimized for the carpet industry. There are different needs because there the density of the fabric is much lower, and therefore we are using a different type of scanning system which is optimized especially for carpets. So all those four detection systems here on the slide, they are always looking like a microscope into the fabric itself. It's always looking for a weft line or for a knitted course. Sometimes we also have to straighten the fabric according a pattern. When you think of lace fabric or when you think of tufted carpet or printed carpet, then it is more important to straighten the fabric according the printed design. This our pattern control system PCS20 can do. Now when we look at our scanning concept, here we see our basic and standard weft straightener. This is the Orthopack R VMC15, and here you already can see that the scanning system is installed at the exit end of the machine, and there are a certain number, 4, 6 or 8 scanners who are there working continuously. Here we have now zoomed into the scanning system. You can see just the scanning system, which is located here at the Weft Straightener, or you can see it here in the outlet of the Weft Straightener. Now a little bit an explanation how the detection system and the system works in connection with the mechanical straightening system. Like mentioned before, you have a number of scanners arranged at the exit end of the Weft Straightener. So the fabric is passing through skew rollers, through bow rollers, and then it is going through the detection system. This detection system is creating the individual signals simultaneously at each position where you have a scanner, and is giving this information into our evaluation software. In the evaluation software, then the total distortion configuration is calculated, it is shown, and this is then compared with the norm. The norm would be to have absolute straight fabric. Then the system is creating the necessary signals for the bow and for the skew rollers to move them to the individual necessary positions in order to eliminate the detected distortions. Finally, the fabric is leaving a Weft Straightener always in straight form. And from this you already can imagine that the detection system is one of the most important parts within such a straightening system, because it is a detection system who actually is giving us the information how the fabric is arriving and how we have to react to the detected distortions. On this slide now we can see the Mahlo scanning concept. Mahlo intentionally has decided that it is the best way to get the information about the distortion via several sensors which are installed across the fabric width. With those technology we have the possibility that we can get the information about the angle of the bypassing weft line at several positions in cross direction continuously and simultaneously. Each scanner is equipped with a digital signal processor which will give the measured angle of the weft line via an interface to our evaluation electronics. The software on the evaluation electronics is then calculating the overall distortion. This is done in parts of second, always new, always again and again. So we can say we are calculating and detecting the fabric distortions in real time, and the result of this is that we have the fastest possible reaction times with our Weft Straighteners. I just mentioned that Mahlo has decided to work continuously and simultaneously with fixed scanners arranged across the fabric width. So you may ask, what would have been the alternative? The alternative would have been to work with a traversing scanning system. This means you take only one scanner, the scanner is traveling in cross direction and takes at various positions, predefined positions, always a snapshot. From this snapshot, the system could calculate the angle related signal. Out of all this information from these individual snapshots, you also could then create the overall distortion. But the problem is that you have to travel in cross direction. Means this sensor will take a certain time to take all the snapshots. It takes on a 3 meter wide fabric approximately 2 seconds to come from one side to the other. When you think of fabric speeds of 70 meters a minute, this means during this period of time, another 2.5 or 3 meters are passing by. This means during that time, there is no renewed distortion measurement. This means also, with such a system, we would not be in a position to do a detection of the distortion in real time. And also, this would mean that you can respond to a dynamic in the distortion, in fast changes in the distortion, much slower than you can do when you have arranged your scanners simultaneously and across the fabric width. So, and on this slide, we have now both systems in comparison. Here you have the traversing system. The scanner is going in cross direction, detecting at several points the distortion. But this means that it always takes, let's say, from here till here, from here till here, in order to create the overall distortion. In between, you have no information if there is a change. If a sawing is coming through, you don't know what is happening before and what is after the sawing. It takes much longer. In our case, we have arranged the scanners side by side. They are measuring always continuously and simultaneously the angle of weft line which is passing by. And so we have constantly, we have this information about the distortion configuration, and we can react immediately on any change in the distortion configuration.